Hello, welcome to another video of CS360. And in this video, we'll talk about Turing machines. Okay. So what are Turing machines? So Turing machines are essentially the way we're going to define a computer mathematically. So this is one of the main topics in this course, and we'll spend our kind of entire second half of the course studying this model of computation. And so just but what you're supposed to take away from it is that this is sort of one relatively simple, relatively elegant way of defining computation mathematically, so that we can prove things about what we can compute with computers. So in order to prove anything about what can be computed, we need to first define a computer, essentially. And this is where Turing machines are going to come in. And now there's many ways of defining computational models. Turing machines are mostly used because they're relatively simple. But all these ways of defining computation, they mostly turn out to be equivalent to one another. So it sort of almost doesn't matter how you define computation, as long as your computational model is sufficiently rich, so that it can capture, for example, using memory and manipulating the memory in arbitrary ways. And also, as long as it's kind of feels somewhat realistic, feels a bit like a machine, you might be able to build. So completely unrealistic models of computation might be ones that are, you just say, okay, by magic, you now get the answer or something like that. Things like that are not going to be equivalent to Turing machines. They're going to be too powerful, I guess. But most ways of trying to define a machine that, kind of takes concrete physical steps in a sense, and but has memory and can manipulate in arbitrary ways. Most definitions of computation that attempt to define it through these, so roughly in that way, end up being equivalent to Turing machines. Okay, so how do we actually define a Turing machine? So the idea of it is that it's similar to a DFA, except that we want to give this DFA unlimited memory. Okay, so remember, a DFA just had a few states. So it looked something like this, maybe. And there were transitions between the states, and the transitions were labeled by what you read from the input. So if we can label this Q0, Q1, Q2, for example. So DFA was something simple like this, and maybe one state here was an accept state or something. And these transitions are labeled by input alphabet symbols. So a Turing machine is sort of like this, but a DFA only has, the only thing it remembers is which state it's in. So it has very limited memory. It has constant amount of memory, basically. If the input size is n, the memory of this machine is sort of still, there's only 3 types of things it's going to remember which of 3 states it's in. That's not even 3 bits of memory. That's sort of like log of 3 memory, sort of like it only remembers which of 3 things it's in. Okay, so this has very little memory, this DFA. We want to expand the DFA by adding memory, right? So how do we do this? So the first thing we do is we so we keep all these states, and this will sort of represent something like the code that we're trying to run. But we will also give this thing access to a tape of memory. This is a bit like a stack of a pushdown automaton, except the shape is kind of a 2-sided tape. This tape, I'm going to draw it. So it has cells, and in these cells are memories. So things like 1s and 0s can be written in the cells. Some of them are blank. Okay, So I'll just leave the blank ones blank. So you can write things in these memory cells, and the Turing machine basically it has a position that it's at along this tape. So, for example, maybe it's currently at this position. So the Turing machine can see the bit that's written in the position it's at, and it's called the head position. So the Turing machine can read this bit 1, okay? And it can also, when it transitions, it can move left or right. So it can move this, the arrow either to the left or to the right when it transitions. And in addition, it can also write to the tape, to the memory. So it can read and write to this one cell that it's at, and then it can move left or right when it's transitioning. So this means that we should sort of label the transitions. The transitions can depend on the state you're starting from. Like here, we're starting from Q0, but it will also depend on what we're reading from the tape symbol. So here we're reading a 1, okay, and then so the transition might depend on this 1, but the transition will also tell us what to write instead, and then whether to move left or right afterwards. So a transition can tell us something like, read read 1, then write a 0, and then transition to the left. So we will denote that by something like 1, write a 0, and then transition to the left. So we'll denote it by a left arrow. Okay, so this 1 transition from Q0 to Q1 tells us the information that if we were at Q0 and we see a 1 at the tape position, at the head position on the tape, then we're going to write a 0. So we're going to write a 0 on the tape, and then we're going to move left on the tape. And then we will also transition to Q1 afterwards. So doing that will basically mean that we it will basically cause us to write a 0 here and to move left, so that we're looking over here now, and we will also be present in state Q1. Okay, so this is how transitions in a Turing machine work. And so you can see that because the Turing machine can move back and forth, it can return, it can move back to the right and read things it wrote again. It can sort of store an unlimited amount of memory along this tape, but it still has a finite number of internal states. So you can think of this as sort of representing finitely many lines of code. So here, maybe a state is very roughly like a line of code, and a transition is very roughly like a go-to statement to tell you to go to a different line of code. But you can also, while you're going to different line of code, you can also manipulate the memory cell a little bit. You can write something in it, and you can move left or right on the memory tape. Okay, so we can visualize Turing machines as kind of like, imagine this whole machine thing. This was shrunk down and was physically sitting as this little machine here, sitting along this tape, crawling on this tape. It's reading this 0 now, but it can crawl to the left or crawl to the right with like a little motor, and it can also read and write on this tape. Okay, so you can imagine this as kind of a physical machine, and that physical machine only has, it's small. It only has a fixed amount of internal memory, the fixed amount of internal states, but the tape is very large, so it can use the tape as sort of external memory. Maybe this is maybe another way to think about it is, imagine this is kind of like just the CPU itself, or something, and this is a large RAM that it can read and write from. Except, I guess in a Turing machine you have to read and write sequentially, so maybe it's more like a hard disk. Anyway, so this is just a mathematical definition. So the notes have like the formal version of it, which is this 7 tuple that specifies all these things that you need. In particular, you need a tape alphabet gamma, which is the set of symbols you can write on the tape. And one of those symbols will be the blank symbol. This is separate from the input alphabet, although it should contain the input alphabet, sigma. The input alphabet is the alphabet of the strings you receive as input. And a Turing machine will receive its input by basically starting with that input written on the tape. So we assume that the Turing machine starts, it reads the input just by crawling along the tape. So the starting position of a Turing machine will be that you're starting at a blank cell is the head position, and to the right of it is the input string. And then there's a blank symbol at the end. So, here we would have sigma equals 0, 1. Okay, and gamma, the tape alphabet, will contain that and the blank symbol and maybe other things. And the Turing machine at the beginning will start here, and then it will be able to read the input if it wants by moving to the right. Okay, it can also do other things. It can move to the left and use this blank space to first write stuff down if it wants. But this is sort of how, so it doesn't receive the input one symbol at a time anymore, like we had for DFAs. Instead, we just put the input in memory. So we put the input in memory and we make the Turing machine go and read it. Okay, so this is the basic gist of Turing machines. So you've already seen in the quiz and in the notes some examples of kind of running a Turing machine. Running a Turing machine is usually very tedious. So there's only kind of a few simple Turing machines where that you can simulate before it becomes kind of unwieldy and too ugly and complicated to draw the machine. But sort of the one nice thing about Turing machines is that they end up being extremely powerful. So you can, well, we don't prove this overly formally in this course, but you can use Turing machines to simulate many other devices. So let's talk about that a little bit. So one thing you can do with the Turing machine is you can simulate a multi-tape Turing machine. So a multi-tape TM. So you can simulate a multi-tape TM. Basically, what is a multi-tape TM? Multi-tape TM is just what you think. It's just the same kind of thing, a Turing machine that has these states and transitions. Okay, it's this kind of thing, but it's attached to now 2 tapes, or maybe more than 2 tapes. I'll draw them vertically here. So it comes with 2 of these, and it has a position on each, and it can independently move left or right on each of the tape. Okay, and so one transition here will kind of depend on what you're reading in each cell, in each that you're at, in each head position on the tapes. So it will depend on both of those, and you will also be able to write to both of them and move left or right independently on either of them. Okay, so this is kind of it gives you a whole extra tape that you can manipulate independently from the first tape in any way you want. But this is no more powerful kind of as a computational model because you can simulate it on a single tape Turing machine. And the idea for that is that you have a single tape Turing machine where you will basically just use an extra marker like a star here. And the marker will sort of split the tape into 2 parts. And then you will kind of try to, well, maybe you'll have, okay, let's think about the details of this. You can have another marker for the beginning and end of these 2 parts. Okay, so let's say we use 3 of these markers. Okay, and now so over here in the first part, we will try to do, we will try to write all the contents of the first tape. So we're trying to simulate this machine over here, and it has 2 tapes. So we will try to use this first part to simulate everything written on the first tape. And this part here, we'll try to use it for the second tape. And okay, fine, but these tapes can be infinitely long. So, you know, how do we fit that in this finite space? The idea is, although the tape is infinitely long, it's all blank. If you want to make it non-blank, the machine will have to just go and write symbols. But after any finite number of steps of this machine, of this multi-tape machine, it can only write a finite number of non-blank symbols. So the non-blank parts of the cell is finite at any point in time. So at any point in time, the non-blank portion of each tape here is finite. So we only need a finite space here for the non-blank portion and a finite space here for the non-blank portion. Now, what if this the non-blank portion in the first tape becomes larger than the space we allotted here between these boundaries? In that case, we can move the star boundary, to the left a couple times, to kind of and then erase it from where it was. So we can kind of expand the space for these two tapes. And so we can run one machine. We can have one machine that is programmed with the code of the starting machine, but also with additional code that kind of goes back and forth. It goes back and forth, and it tries to add labels in these subsections of its tape. It adds the labels to help itself remember where the tape head is. So I mean, okay, let's give an example. Suppose the string that's written here is 0, 1, 0, 1, 1. Okay, so suppose this is the string it's written here, and here it's all zeros. And suppose we're that's what's written on the first tape and the second tape. And suppose that we're supposed to be kind of on this one. We're supposed to be reading this one for where this arrow is. So then we can use a new alphabet symbol that basically kind of highlights this one, circles it. So we can have a circled one. Instead of a 1 symbol, we'll have a circled 1 symbol that kind of highlights it so that the Turing machine can remember where it was. And similarly, we can have some circled 0 here for where the Turing machine is supposed to be. So we are expanding the tape alphabet. We're expanding the alphabet used to write in the tape by doing this. And now this Turing machine can basically have code that kind of goes back and forth. It says, move left until you find this first star, and then start moving right one by one. So kind of move to the right until you find the circled position. And then, okay, use your internal states here to remember that you're seeing a 1. And then, okay, keep going to the right until you see a star, and then until you see another marked position, and use your internal states to remember that you saw a 1 and then a 0. And then, but also use your internal states to remember which internal state of the original machine you're simulating you should be at. Okay, and then find which transition you're supposed to take. And you kind of do all of that with only finitely many internal states of the new machine, where you have some intermediate states that handle this, this part where you keep going all the way to the left to find the first star, and then going all the way to the right to find the circled items and memorizing them. Okay, and then so using this kind of strategy and as well remembering the subroutines that can expand the space for these tape cells when you need to, you can simulate a multi-tape machine with a single tape Turing machine, but that used an expanded alphabet. So the tape alphabet was now expanded. We've added new symbols. Basically, if before the tape alphabet was 0 and 1, now we kind of have 0, and 1 and star, and like this circled 1 and this circled 0. So we have a larger tape alphabet. But we can simulate a Turing machine that has a large tape alphabet with another Turing machine that has a small tape alphabet. So we can, with even more simulation overhead, we can go back to very simple tape alphabet. And the way to do this is basically to just, express these different tape symbols as in binary. So like, we can rename these 1, 2, 3, 4. Let's say 0, 1, 2, 3, 4 or something. And then we can write these in binary. Okay, and we can kind of just use more cells to write these symbols by writing only 0 or 1 in each cell and doing everything in binary. So the size of the tape alphabet actually doesn't matter for the power of the Turing machine either. And many variants of Turing machines turn out to just give you no more power than a single tape Turing machine. So although you might imagine that you can, let's say, add some notion of random access memory, like a RAM, where you don't have to read the memory cells sequentially, you can jump in memory. You might imagine that that can give you some more power, but you can simulate that on a Turing machine just more slowly, just kind of, instead of jumping to a position, you would keep going to the right one more until you get to the desired position, for example. And various other simulation tricks like this that we won't go through. So a Turing machine is kind of a very powerful model of computation that whenever you try to make it more powerful, it turns out you failed. You kept it at the same power level. Whatever other attachments or enhancements you want to give it, you can simulate them already with a single tape Turing machine, so you never needed them in the first place. Okay, so in this course, we will often think of Turing machines as computer programs, because that's more or less what they are. They're just a mathematically formal version of a computer program. Oh yeah, and I guess I should mention, so I've described how a Turing machine runs. In the notes, we also talk about when a Turing machine accepts or rejects. So the Turing machine will have two special states, one called the accept state and one called the reject state. And generally, any Turing machine must have both of these states, one for accept and one for reject. And you cannot transition out of them. So once you go to the accept state, the run stops. The Turing machine stops running. And it's said to have accepted. And if it goes to a reject state, it stops running and it says to have rejected. Sometimes Turing machines run forever. They don't have to ever reach an accept or reject state, depending on the input, depending on what's written on the tape when they start running. And that's sort of similar to a computer program that either returns true or returns false. And sometimes if you have a badly written code, then the function you're calling never returns true or false because it just never terminates. It hits an infinite loop. So that's, of course, another possible outcome for your function. Yeah, so as we've defined them, Turing machines never crash. I mean, they always have some transition to go to. Or, we can take, if we don't want to write out all the transitions, we can say that any transition we don't write means that you go to the reject state. But there's no notion of crashing that's independent, that's different from rejecting. Okay, so it's different from returning false. There's no, in a computer program, you might say, okay, there's crash, which is some different output than returning false. But in Turing machines, there's return true, return false, and keep running forever without returning. These are the possible things you can do. Okay, so maybe another important notion of Turing machines is that so we usually think of them as running on an input string, and the input string is what's written on the tape when you start running. Okay, so when you have a Turing machine, we'll denote by M. Generally, you are going to run it on some string W, which is going to be a finite string, and it's written on the tape when you start running M. So what if you wanted to give this? So if we think of the machine as a program, you can ask, what if I wanted to give it two strings as input? So to give it two strings, I can, of course, just basically give it one string and have a separator symbol in the middle of that string. So basically, what I can do is I can write one string. Like I suppose I wanted to give it 1 1 0 followed by 0 1. Then I can write 1 1 0, and then I will put some separator symbol like this pound symbol, and then the other string, and then followed by blank spaces, and then the Turing machine will start in this first blank to the left of the input. So I can. So this, of course, expands the tape alphabet, or the input alphabet even. So basically, this is saying that we can represent two strings, x and y. We can represent two strings using one string that's basically x, and then some new symbol, and then y. Okay. So so in that way, we can always imagine a program takes two strings like this if we want. And then if we want, we can encode everything in binary. So, I mean, we don't have to introduce a new symbol. We can just use binary characters and like maybe some ASCII notation or something, and reserve a special symbol for the separator between strings. The details of that don't really matter, so we'll generally just ignore them. But yeah, we can sort of have the machine take in two strings as input if we want. And also in this course, we will use kind of these angle brackets to denote representing something as a string, some finite thing as a string. So for example, if we have a context-free grammar G, not the language, but the grammar is finite. The grammar has finitely many variables, finitely many rules. Each rule is finite. So the grammar can be specified using a string, using a finite string, the way you would, you're using some specification language as you're used to in programming. So, we will denote the stringification, I guess, of the grammar G by angle bracket, G surrounded by angle brackets. So when we surround things with angle brackets, we just mean the stringified version. And especially useful will be to represent Turing machines as strings. And Turing machines, remember, are finite in description. So the tape is infinite, but the tape starts blank or starts containing the input. To describe the machine itself without its inputs, just the machine, we don't need to talk about the tape. We don't need to represent the tape. We only need to represent all the transition rules between the states. So we only need, that finite list of transition rules. We need which one is the start state. We need which ones are the accept and reject states. And then we need these arrows, these transition rules that say things like this. So we need all of the arrows. But there's only finitely many, a finite amount of information here. So we can denote all that finite amount of information in a finite string, and that string will be angle bracket M, where M is the Turing machine. So M is the mathematical object, and angle bracket M is the string. Okay, so we can write, for example, if we want to write M running on a string W, we can write M of W to represent kind of M running on W. Like the program subroutine call to M on input W, fine. But we won't. But angle bracket M is a string, right? So we won't. We can't run a string on anything, right? So M is like a program. You can write M of W, and we interpret that as running a program. Angle bracket M is a string. Okay. So usually this won't be too confusing. Just if you, we'll generally put angle brackets everywhere to denote turning everything into string all the time. One particularly useful thing you can do with Turing machines is that you can have a universal Turing machine. Okay, so the universal Turing machine is a Turing machine that takes the description of another Turing machine as input and then basically simulates it. So in particular, we will assume that M. So if actually, sorry, let's denote this machine by U. This is a TMU, and then it will take as input basically this pair of MW in stringified version, where M is a Turing machine, and then W is a string. And then it will except if M accepts W, and then it will reject if M rejects W. Okay, and then it will loop. Loop meaning never terminates. So we use the term loop to mean that it never accepts or rejects. So it will loop on this input if M of W loops. Okay, so it never terminates if M of W never terminates. So this universal Turing machine, what it does is it's basically an interpreter. It takes as input code, like a string that represents a machine, and then it takes as input to that machine, and then it basically simulates that machine on that input. So it's basically running the code M on W, and so this is kind of interesting that you can do this with the Turing machine. The notes try to convince you of this fact. It's a little bit complicated, but not so bad, I guess. Just everything with Turing machines is a bit annoying to do explicitly. We can imagine two parts of the input tape for our machine U. One part where we will write the description of M, and one part where we will write W. So here we can write W. So we can write, whatever the string W is, and then on the left we can write M, and then we can sort of use extra tape alphabet symbols to highlight the states of M. So we can have these special places that are the states of M. And I don't know. We can also mark one of these states if we're at that state. So that will allow us to keep track of being at that state. So imagine kind of marking that we are here using by changing this symbol to some other symbol. Okay, so that will tell us which state we're in. Okay, so okay, fine. So I mean, I guess we should store the state name somewhere as well. So the state's name, which is basically a number, we will probably need to represent that number in binary and kind of write it next to the state here in the tape. Okay, so we will want a marker for which state we're at, and then what we will do, what the Turing machine U will do, is we'll basically sort of go back and forth, kind of find this special state that we're at, try to look for a transition rule. So there'll be another part here with the transition rules of M. Okay, so that's part of the description of M. So there'll be transition rules of M. So this Turing machine will basically have to find a transition rule that matches both the starting state that's highlighted in the tape, and also the position of the tape that we're at. So I guess we can use a second tape if we want. Maybe a two-tape Turing machine. So we will basically want to kind of go back and forth, find the transition rules that matches that matches both the highlighted state we're in, like we're in state Q3 right now, and also we are seeing at the tape head the position, the string 1 or something, and then we want a transition rule that tells us what to do from there, and that transition rule is somewhere in the description of M. So if we have the description M over here, we will try to look for a transition rule that matches exactly that. So we'll have you will have code for this matching process that matches the name of the state Q3 and what we're seeing in the tape, basically, which is 1, and basically matching that to a transition rule of U. And then we will have to follow what the transition rule has to do. So the transition rule might say, now write a 0 and now move to the left. So we can write a 0 and we can move 1 to the left so that we point here. Okay, and then after that, we will have to transition to a new state like Q7. So then that will mean that we will have to erase this marker and put it at a different state. Okay, so anyway, I'm not sure the explanation is very clear, but the idea is that we can define a complicated enough Turing machine U that will simulate the behavior of M, even though M is itself just described on the tape. So M itself is just this list of transition rules and list of names of states. It's sitting on U's tape, on the tape of U. Okay, and yet U is simulating the behavior of that machine that's written on its tape. And I guess it's using here a second tape on which is supposed to represent the tape of M. Of course, we can put that all on one tape. We saw that we can simulate two tape Turing machines with one tape Turing machines. So we will assume that U actually has only one tape. Okay. So this is called a universal Turing machine. And you can think of this as roughly an interpreter or I guess, it's a machine that takes code as input and runs that code. And the thing with an interpreter is it's although you can run an input program that's given to you, you don't really know what it's going to do until you actually, finish doing it. So, although our machine U is going to be able to simulate M on W step by step, it's not going to be able to tell in advance whether U is ever going to halt or whether U is not going to halt. So this is going to be kind of one of the key lessons in this first part of the course on Turing machines, that you can't tell whether an input machine is going to halt or not, whether it's you can simulate it, but if it didn't finish running yet, you can't know whether that's because whether it's still going to finish running soon or whether it's never going to finish running. So we will talk about that, I guess, in the next video. All right.